Imagine it's January 1942. Deep in the heart of Seattle, Boeing Plant 2 is supposed to be the beating heart of America's war effort. Its mission is simple, monumental, and utterly vital: to pump out so many B-17 flying fortresses that their sheer numbers would literally darken the skies over Nazi Germany. But on the factory floor, there's no triumphant roar of production. There's only the grinding, deafening silence of failure. It looks less like an assembly line and more like an industrial traffic jam. 63 B-17 bombers, 63 magnificent, deadly promises, sit frozen in various stages of incompletion. Each one is a monument to a promise America couldn't keep. The numbers were horrifying. The Army Air Forces, desperate for air power, had ordered 3,615 bombers to be delivered throughout the year. 3,615. And how many had Boeing managed to deliver? 9. Just 9. General Henry Hap Arnold, the commanding general of the Army Air Forces, wasn't just disappointed, he was furious. This wasn't a spreadsheet problem, it was an existential threat. On January 15th, he met with a room full of terrified Boeing executives, and he didn't mince words. The message he delivered was brutally clear. Without bombers, there would be no strategic bombing campaign. Without a strategic bombing campaign to cripple German industry from the air, American soldiers would have to face an entrenched, fully supplied Nazi war machine on the ground for years. The math was simple, and it was terrifying. Every day of delay would be paid for in blood. So what was the problem? It wasn't manpower. In a patriotic frenzy, Boeing had hired over 30,000 workers in just 6 months. Many of them were women, Rosie the Riveters, who had never set foot in a factory before, but who were now the backbone of the war effort. It wasn't materials either. The aluminum giant Alcoa was shipping in raw materials faster than Boeing could possibly use them. Mountains of gleaming aluminum sheets sat waiting. The crisis was something deeper, something nobody had anticipated. The bombers themselves, they were just too damn complex to build quickly. Think about this. Each B-17G model required 140,000 individual parts. The wings alone were a nightmare. A single wing demanded 12,000 rivets per side. These weren't just simple fasteners. They had to perfectly connect 7 overlapping layers of aluminum skin to a complex internal framework. And that framework had to be strong enough to withstand the unimaginable stresses of combat maneuvers, pulling up to 6 Gs while dodging enemy fighters. The traditional assembly methods, the ones perfected on smaller, simpler aircraft, had simply collapsed under the weight of this complexity. Every morning at 5 a.m., Philip Johnson, Boeing's production manager, would walk the factory floor, clipboard in hand, and watch the same soul-crushing nightmare unfold. He'd stop at Wing Assembly Station number 4. There, 17 workers were clustered around a single massive wing section. They weren't working together so much as they were getting in each other's way. The choreography was insane. A riveter would finish a seam, step back, and immediately another worker would need to access the exact spot he had just vacated. Then a third worker needed that same position for a different rivet line. It was a chaotic ballet of inefficiency. Johnson timed it himself, clicking his stopwatch with a growing sense of dread. 20 hours and 14 minutes. That's how long it took to complete one wing assembly, from a bare framework to the final polished rivet. 20 hours. 20 hours. Over the skies of Germany, the British Royal Air Force was losing bombers faster than that. The consequences of this bottleneck rippled across the entire war. Every Luftwaffe fighter that went unchallenged because American bombers weren't in the sky meant more merchant ships, full of vital supplies, were being sunk in the cold Atlantic. It meant more factories in the Ruhr Valley could run at full capacity, churning out tanks and guns for the Eastern Front. It meant more time for Nazi Germany to consolidate its iron grip on Europe. Boeing's engineers, the best in the world, had tried everything they could think of. They redesigned tool access points. They created specialized jigs and fixtures to hold the wing sections. They even experimented with different crew sizes, thinking maybe fewer workers would reduce the congestion. Nothing worked. The fundamental problem was written into the aircraft's DNA. The rivet pattern, specified in the holy grail of engineering blueprints, required work crews to access the same physical space in an overlapping sequential order. You couldn't parallelize the work. You couldn't just throw more workers at it to speed it up. It was a bottleneck designed by geniuses, a perfect trap. By late January, the whispers began. Boeing executives started having quiet, desperate conversations about the unthinkable, telling the Army they simply couldn't meet the production targets. Some even suggested bringing in rival companies like Douglas or Consolidated to take over primary production. It would be a humiliating, catastrophic failure. On January 28th, a classified memo circulated among senior management. The subject line read, "Crisis Assessment, B-17 Program Viability." The subtext was clear. Nobody wanted to be the person who lost the war because they couldn't figure out how to rivet a piece of aluminum fast enough. Let's zoom in. Walk into Wing Assembly Station 4 on any given morning, and here's what you'd see. What looked like organized chaos that wasn't actually organized. The wing section, a massive skeleton of aluminum ribs and spars spanning 32 feet, lay on an enormous jig. Waiting beside it were 7 layers of aluminum sheeting, each one precisely cut and pre-drilled with thousands of holes, ready to be attached in a very specific sequence. The process was supposed to start from the wing root, the thick part that would eventually bolt to the fuselage, and work its way outward toward the delicate wingtip. Sounds straightforward, right? It wasn't. The engineering blueprint, a document treated with near religious reverence, specified that the rivets had to be installed in perfect parallel rows running from the wing's leading edge back to the trailing edge. Row 1, then row 2, then row 3, marching backward like disciplined soldiers. From a structural perspective, this made perfect sense. Each row of rivets reinforced the one before it, creating an overlapping shingle effect that brilliantly distributed stress loads across the entire wing surface. The engineers at Boeing's developmental center had calculated every single rivet's position to optimize the strength-to-weight ratio. On paper, it was beautiful, a masterpiece of structural engineering. On the factory floor, it was a disaster. Here's why. To install row 1, you needed a 2-person team. A riveter worked from the top surface, while a bucker, the person holding a heavy backing bar called a bucking bar, worked from below, reaching through the wing's internal structure. They had to be perfectly synchronized, a dance of man and machine. The riveter's pneumatic gun, a beast of a tool, drove the rivet through the pre-drilled holes with 3,000 pounds of force. At the exact same instant, the bucker's bar had to be pressed firmly against the rivet's tail on the opposite side. The force would shape the molten aluminum into a perfect mushroom head, locking the sheets together forever. Miss that timing by even half a second, and you got a loose rivet, a useless rivet, a rivet that had to be painstakingly drilled out and replaced. Each mistake cost 3 minutes. Multiply that across 12,000 rivets, and a few small mistakes quickly became a catastrophic loss of time. But the real nightmare began when it was time to start row 2. To access row 2's rivet line, the new work crew needed to position themselves exactly where row 1's crew had just been working. Except, row 1 wasn't completely finished. Quality inspectors needed to check every 10th rivet with a borescope, a tedious, painstaking process that took a full 15 minutes per wing section. So, the row 2 crew waited and waited. Meanwhile, the row 3 crew, already suited up and ready to go, stood around, burning daylight, watching the clock tick. The production schedule was a fantasy, calling for parallel work streams that the physical reality of the wing's geometry made utterly impossible. You simply couldn't fit enough people around the structure to rivet multiple rows at the same time. And then there were the tools themselves. The rivet guns weren't delicate precision instruments. They were industrial pneumatic hammers that vibrated with such force they shook your entire body when fired. The compressed air hoses that powered them snaked across the factory floor like demented pythons, constantly getting tangled with electrical lines for the inspection lights, tripping up workers who were just trying to move from one station to another. Think about it. One riveter moving from position A to position B had to unplug his air hose, carefully coil it up, navigate around 3 other workers, find a new air coupling station, plug back in, and only then could he resume his work. That 30-second process happened 70 times per wing section. Then there was the heat. Seattle in January wasn't warm, but the factory was a furnace. 17 workers clustered around a single wing section, each one generating body heat. Each pneumatic gun firing compressed air added even more warmth to the enclosed space. Think about it. One riveter moving from position A to position B had to unplug his air hose, carefully coil it up, navigate around 3 other workers, find a new air coupling station, plug back in, and only then could he resume his work. That 30-second process happened 70 times per wing section. Then there was the heat. Seattle in January wasn't warm, but the factory was a furnace. 17 workers clustered around a single wing section, each one generating body heat. Each pneumatic gun firing compressed air added even more warmth to the enclosed space. The aluminum sheeting, an excellent conductor, absorbed all that heat and began to expand microscopically. Not by much, just 0.03 of an inch per 10-foot section. But when you're trying to align pre-drilled holes that have a tolerance of only 0.02 of an inch, that expansion was a disaster. Holes didn't line up. Riveters ended up spending 15% of their time using tapered reamers to enlarge holes that had shrunk out of alignment as the metal cooled. None of this, the tangled hoses, the weighting, the thermal expansion, appeared in the engineering specifications, because nobody in a clean, quiet office had ever anticipated 17 people working in such close proximity for such an extended, exhausting period of time. Frank Szymanski did not look like the man who would change the course of the war. He was 31 years old, 5'7", with hands that were permanently stained with aluminum dust and cutting oil. Before Pearl Harbor, he'd worked at a Chrysler plant in Detroit, installing door panels on Windsor sedans. It was repetitive work, mindless work, the kind of job where your hands knew what to do long before your brain caught up. When Boeing started its massive hiring surge in late 1941, Frank packed up his wife and 2 daughters, moved to Seattle, took a room in a boarding house near the plant, and joined the swing shift at the now infamous Wing Assembly Station 4. He started work at 4 p.m. and finished at midnight, 5 days a week, sometimes 6 when production quotas were particularly desperate. What made Frank different wasn't his riveting skill. Dozens of other workers could match his speed and precision. What made him different was that Frank couldn't stop watching. He didn't just see his own work, he saw the whole broken process. Most riveters focused on their immediate task: line up the gun, squeeze the trigger, move to the next rivet, repeat 400 times a shift. But Frank saw the entire ballet. He noticed that Jenkins, working on row 3, was always waiting for Patterson to finish row 2. He noticed that Patterson was always waiting for the quality control team to clear row 1. He saw, with a clarity that seemed to elude everyone else, that the prescribed sequence created a cascade of delays that compounded geometrically as you moved across the vast surface of the wing. On February 4th, during his midnight break, Frank sat on an overturned parts crate, eating a bologna sandwich and staring at a completed wing section that was being moved to final assembly. Something about it bothered him. The rivet pattern looked perfect from a structural perspective. Each row neatly overlapped the previous one, creating that shingle effect the engineers loved so much. But Frank kept thinking about his old job at Chrysler. When they installed door panels, they didn't start at one edge and work their way across. They started at 4 corners simultaneously and worked toward the center. Why? It was simple. Because it allowed 4 workers to operate in parallel without ever getting in each other's way. The geometry of the door panel made parallel work possible. He looked back at the wing schematic posted on the station's bulletin board. The rivet pattern ran in those perfect, straight lines, from leading edge to trailing edge. Parallel rows marching across the wing surface. But the wing itself wasn't a flat rectangle. It was a complex, 3-dimensional structure. It had depth. It had internal ribs creating separate chambers. It had access points at specific, designated locations. And then the idea struck him. A question so simple and yet so profound. What if the rivet sequence matched the wing's actual geometry instead of treating it like a flat sheet of paper? What if you started at multiple points simultaneously? Points chosen not for their position in a theoretical grid, but because they gave workers the maximum possible physical access without overlapping. Frank grabbed a pencil from his pocket and started sketching on the back of his time card. Instead of those neat straight rows, he drew a pattern that looked almost random. He drew clusters of rivets around the strong internal structural ribs where access was easiest. Then he drew radiating lines connecting those clusters, following the natural contours of the wing's internal structure. It looked wrong. It looked like someone had spilled a box of rivets on the blueprint and just decided to leave them where they fell. But as Frank traced the pattern with his calloused finger, he realized something crucial. With this pattern, you could have 5 workers riveting at the same time, and none of them would ever need the same physical space. Worker 1 could be at the wing root, inside the main spar chamber. Worker 2 could be mid-wing, accessing the interior through an inspection panel. Worker 3 could be working on the trailing edge, which was shallow enough for top-down riveting without even needing a bucker. They'd never intersect. The traffic jam would disappear. The structural implications worried him, though. He knew the engineering blueprint specified that parallel row pattern for a reason. Words he only half understood, like load distribution and stress concentration, echoed in his mind. But then he thought about something else he'd noticed on the floor. Rivet failures almost never happened where 2 rows met. They happened at transition points, where the wing skin changed thickness, or where cutouts for the fuel tanks interrupted the neat pattern. The rows themselves weren't magical, they were just one way to distribute fasteners across a surface. Maybe, just maybe, they weren't the only way. Frank knew what would happen if he, a lowly riveter, walked up to a production supervisor with his scribbled time card. They'd smile politely, pat him on the back, tell him the brilliant engineers had spent months calculating those rivet positions, and send him back to his station. The hierarchy in Boeing Plant 2 was rigid. Engineers designed, supervisors managed, workers assembled. Nobody expected innovation from a guy whose job title was Riveter Grade 2. But Frank had one advantage. He worked the swing shift. And the swing shift supervisor, a man named Bill Hendricks, was different. Hendricks had started as a sheet metal worker himself before being promoted in 1940. He still had the grit of the factory floor under his fingernails. And he actually listened to the workers, a trait that made him either remarkably progressive or dangerously naive, depending on which manager you asked. On February 11th, Frank caught Hendricks during the 8 p.m. shift change, and, his heart pounding, showed him the sketch. Hendricks stared at it for a long, silent time. Then he said something Frank hadn't expected. "This violates every structural loading principle Boeing uses. You know that, right?" Frank nodded. He knew, or at least he suspected. Hendricks kept talking, his voice low but intense. "The parallel row pattern isn't arbitrary, Frank. When the wing flexes under load, stress concentrates along predictable lines. The rivet rows are positioned perpendicular to those stress lines. That's foundational stuff. It's in every aerospace engineering textbook published since 1927. The principle Hendricks was describing was the gospel of modern aerospace engineering. It came from the work done by the legendary Theodore von Karman and his team at Caltech in the late 1920s. They had proven, mathematically, that fastener patterns in load-bearing structures needed to follow what they called stress trajectories, the invisible lines of force that flow through metal under pressure. A B-17 wing carrying 6,500 pounds of fuel plus the structural weight of 4 massive engines experienced enormous bending stress during flight. The bottom surface was under tension, trying to stretch apart. The top surface was under compression, trying to squeeze together. Right along the middle, the neutral axis, the stress approached zero. Von Karman's equations showed that fasteners needed to be densest where the stress was highest, and could be sparser where stress was minimal. The parallel row pattern achieved this perfectly. Each row corresponded to a specific stress magnitude, with rivet spacing meticulously calculated to match the load requirements. Frank's pattern threw all of that out the window. His clusters placed dense rivet concentrations around the structural ribs, not the stress lines. His radiating connections followed the convenience of worker access, not the calculated load paths. From a classical engineering perspective, it was gibberish, utter nonsense. Sure, the wing might hold together during taxi tests, it might even survive the first few flights. But under the sustained, violent stress of combat, microfractures would inevitably develop where the rivet pattern failed to match the stress pattern. Those fractures would propagate, the wing would fail, men would die. Hendricks explained all of this to Frank right there on the noisy factory floor, shouting over the rhythmic roar of the pneumatic guns. Then he asked a question that changed everything. But did von Karman ever consider assembly efficiency as a structural factor? Frank looked confused. Hendricks leaned in closer. Think about it. If it takes us 20 hours to rivet a single wing, and we're making mistakes because our workers are exhausted and cramped and tripping over each other, how many of those 12,000 rivets are actually installed to perfect specification? How many are slightly loose because the bucker missed his timing? How many holes are slightly reamed out because they didn't align perfectly? Your pattern might be theoretically weaker, Frank, but what if it produces practically stronger wings because the installation quality is perfect? This was heresy. Absolute heresy. Boeing's quality control processes were built on the assumption that workers followed the procedures correctly. The procedures were designed around the engineering specifications. If wings were failing quality checks, you didn't change the design, you retrained the workers, or you fired them and hired better ones. You didn't redesign the damn aircraft to accommodate worker limitations. That was backwards thinking. That was letting the tail wag the dog. But Hendricks had seen something in his 3 years as a supervisor. He'd seen that theoretical perfection and practical reality diverged more than any engineer in an office wanted to admit. He'd seen riveters so exhausted by hour 18 of a wing assembly that their hands shook uncontrollably. He'd seen buckers miss their timing because they'd been crouched in the same agonizing position for 40 minutes and their legs had cramped up. He'd seen quality inspectors reluctantly approve marginally loose rivets because rejecting them would mean another 2-hour delay, and the production quotas were already an impossible dream. What if Frank's impossible pattern, by slashing assembly time and reducing worker fatigue, actually produced more reliably perfect installations? Hendricks folded Frank's time card sketch and carefully put it in his breast pocket. "I'll talk to someone," he said. Frank went back to his rivet gun, expecting nothing. Hendricks didn't go to the chief engineer. That would have been professional suicide. Oliver Eccles, Boeing's head of engineering for the B-17 program, had a reputation for eating floor supervisors who dared to question his designs for breakfast. Instead, Hendricks went to a man named Donald Douglas, no relation to the rival aircraft company. Douglas was an assistant production manager, and he was also 3 weeks away from being fired if production numbers didn't improve dramatically. Douglas was a man desperate enough to listen to a crazy idea. On February 18th, Douglas looked at Frank's sketch for about 30 seconds before tossing it back on his desk. "This is garbage. Get it out of my office." Hendricks didn't move. He pulled out his own notebook and showed Douglas something else. The assembly time logs from Wing Station 4 over the past 6 weeks. Every single wing had taken between 19 and 22 hours to complete. Not a single outlier. Not one crew that had magically figured out how to go faster. The bottleneck wasn't the workers, it was structural, built into the process itself. Douglas stared at the numbers, then back at the sketch. His expression softened from anger to weary resignation. Even if this works from an efficiency standpoint, Hendricks, Eccles will never approve it. Never. He'd rather shut down the entire plant than rivet a wing in a non-standard pattern. Here's what Douglas understood that Hendricks didn't fully grasp. Boeing was weeks, maybe days, away from losing the B-17 contract entirely. Consolidated Aircraft had been lobbying the Army Air Forces hard, arguing that their B-24 Liberator was easier to manufacture and could be produced in much higher numbers. General Arnold was listening. If Boeing couldn't demonstrate a dramatic, almost miraculous production improvement by March 15th, the Army would redirect its massive orders to Consolidated and other manufacturers. Boeing would keep some production, but they would lose their coveted position as America's primary heavy bomber supplier. That meant massive layoffs. That meant Seattle's economy, now completely dependent on the war effort, would collapse. And it meant Donald Douglas would lose his job anyway. Backed into a corner, Douglas made a decision that violated about 17 different Boeing protocols. He authorized a test, a secret test, without engineering approval. But he couldn't do it during the day shift, not with senior management constantly walking the floor. He couldn't even do it on the swing shift because too many people would see. He scheduled it for the graveyard shift, February 21st, starting at the stroke of midnight. He pulled a wing section that had already failed quality control for unrelated reasons, a damaged internal spar that made it unsuitable for flight. That way, if the test went catastrophically wrong, they weren't wasting a perfectly good wing. He assigned Frank and 4 other veteran riveters from the swing shift who'd volunteered for the clandestine operation, and he told absolutely nobody else. The test began at 12:14 a.m. Frank had spent the last 3 days refining his pattern, working out exactly which rivet clusters went where, calculating sequences that would let all 5 workers operate simultaneously without a single collision. He'd even color-coded the blueprint: red for worker 1, blue for worker 2, green for worker 3, yellow for worker 4, and purple for worker 5. Each color represented a physical zone that didn't intersect with any other color zone. The workers could literally rivet at the same time without coordinating, without waiting, without ever bumping into each other. Watching it happen was surreal. Traditional riveting had a rhythm, a sequential, predictable logic. This looked like controlled chaos. One worker was deep inside the main spar cavity. Another was underneath the trailing edge. A third was working topside near the leading edge. They weren't following rows, they were following clusters, and those clusters seemed scattered at random across the wing's surface. 30 feet away, Douglas stood with a stopwatch, chain-smoking Lucky Strikes. Hendricks stood next to him, silent, his fists clenched. Every 15 minutes, Douglas would check his watch and scribble down the time in his notebook. At the 2-hour mark, under the old system, the wing should have been maybe 20% complete. It was 45% done. The workers themselves started to realize something extraordinary was happening. They weren't waiting, not for each other, not for inspectors, not for access. Every single rivet position Frank had marked was genuinely, immediately accessible without interference. The pneumatic hoses weren't tangling because the workers weren't crossing paths. The heat buildup was lower because they weren't all clustered in one area. The aluminum wasn't expanding as much because 5 distributed heat sources created less concentrated thermal load than 17 sources crammed into one spot. At 2:21 a.m., just 127 minutes after they started, the final rivet was installed. Douglas clicked his stopwatch. He didn't say anything. He walked up to the wing and started inspecting rivets at random, pulling out his borescope and checking for proper mushroom formation. Hendricks held his breath. Frank stood there, covered in a fine layer of aluminum dust, trying desperately to read Douglas's face. Douglas inspected 30 rivets before he could trust his own eyes. Each one was perfect. The mushroom heads were uniform, properly seated, with no visible gaps between the aluminum sheets. He called over Jimmy Chen, the graveyard shift's lead quality inspector, without explaining what he was looking at. Chen, a meticulous and notoriously grumpy inspector, grabbed his toolkit and started a full inspection protocol, the same one he'd run on 200 previous wings. He checked rivet spacing with calipers. He used a thickness gauge to verify the sheet metal compression. He tapped each rivet head with a small ball-peen hammer, listening for the solid thunk that indicated a proper seating versus the hollow ping of a loose rivet. 40 minutes later, Chen looked up, bewildered. "This passes," he said. "I don't know what crew did this, but it's the cleanest work I've seen in months." Douglas told him how long it took. Chen thought he was joking. Then he thought the stopwatch was broken. Then he started his inspection all over again, because wings that were riveted that fast shouldn't be this clean. There had to be mistakes, rushed work, something wrong. He found nothing. The wing was perfect. Better than perfect, actually. Chen had been inspecting B-17 wings since July 1941, and he kept a private log of defect rates that he never showed to management. The average wing had around 140 rivets that needed some kind of attention during quality control: loose rivets, misaligned holes, various installation errors. This wing had 11. Just 11, less than 1/10 the normal defect rate. But passing a visual inspection didn't mean the wing would survive under real flight loads. The rivet pattern was still, from a structural engineering standpoint, completely and utterly wrong. Douglas knew they needed a real test, the kind that required massive equipment and authorization he absolutely did not have. At 3:30 a.m., he made another unauthorized, career-ending decision. He called the night crew at Boeing's structural test facility in Building 7 and told them to prepare for an emergency stress test. He didn't mention that the wing used an unapproved, heretical rivet pattern. He just said they needed rush testing on a wing section for production validation purposes. The test facility had a monster of a machine, a massive hydraulic press that could apply up to 150,000 pounds of force to a wing section, bending it upward and downward to replicate the violent stresses of flight maneuvers. The standard B-17 qualification, laid out in Army Air Force's specification R1816B, required wings to withstand loads equivalent to 6.2 times the aircraft's maximum weight, 6.2 Gs, without any permanent deformation. That was the safety margin. Douglas was about to test a wing that violated R816B in every possible way, using a facility that wasn't authorized for non-standard testing at 4 o'clock in the morning when nobody was watching. They mounted the wing section in the test frame at 4:15 a.m. The hydraulic press engaged with a low hum, applying upward pressure that began to bend the wingtip skyward. Douglas watched the strain gauges, his knuckles white. At 1 G equivalent load, the wing flexed normally. At 3 G, still normal. At 6 G, the deflection matched the specification exactly. At 6.2 G, the official qualification threshold, the wing held. No creaking, no rivets popping, no spider webs of stress fractures forming in the aluminum skin. Douglas, his heart hammering, told the operator to keep going. At 7 G, the wing was still structurally sound. At 8 G, individual rivets near the wing root started showing strain, but that was expected. The wing root carried the highest loads and was designed to be the first failure point. At 8.4 Gs, the test was terminated. Not because the wing failed, but because Douglas was terrified of breaking the multi-million-dollar test equipment. They released the hydraulic pressure. The wing gracefully returned to its neutral position with no permanent deformation. 0. A properly designed wing should have shown some microscopic permanent set after being loaded to 8.4 Gs. This one didn't. It behaved as if it had only been stressed to maybe 5 Gs. Chen ran his inspection protocol again, meticulously checking every rivet that had been under maximum load. None had loosened. None showed any evidence of microscopic slippage. The wing was somehow stronger. Stronger than wings built to the official, perfect pattern. Douglas stood there at 5:47 a.m., the dawn light beginning to filter through the grimy factory windows, trying to understand what he was seeing. Frank's pattern had placed the rivet clusters around the main structural ribs, and those ribs were the primary load-bearing members of the entire wing. By concentrating the fasteners exactly where the structure was strongest, Frank had accidentally created a pattern that reinforced the wing's natural load paths, instead of fighting against them. The radiating connections between the clusters acted like secondary stress distributors, channeling the loads away from weak points. It wasn't random at all, it was organic. It matched the way forces actually flowed through the structure, not the way engineers in an office thought they should flow. By 6 a.m. on February 21st, Douglas knew he had to take this to someone who could actually authorize a full-scale implementation. Not Eccles, the chief engineer, who would kill it on principle alone. He went straight to the top. He went to James Murray, Boeing's vice president of operations, waking him up at his home in the wealthy Laurelhurst neighborhood. Murray arrived at the plant at 7:15 a.m., still in his weekend clothes, and demanded to see everything: the test data, the inspection reports, the time logs. He watched Douglas's hands shake as he confessed everything they'd done without authorization. Murray's face was an unreadable mask of stone. Then, Murray asked the only question that mattered. Can we train 200 riveters to use this pattern by Monday? Douglas hadn't even thought that far ahead. He'd been so focused on proving the concept worked that he hadn't considered the logistics of scaling it. But Murray was already doing the math in his head. If one wing assembly went from 20 hours to just 2 hours, and Boeing had 42 wing assembly stations, that meant they could increase wing production by a factor of 10 without hiring a single additional worker. Wings were the bottleneck. Fuselages were being assembled faster than they could be mated to wings. Tail sections were stacking up in a corner of the factory, waiting for completed aircraft. The entire production line was being choked by the speed of wing assembly. Fix that, and everything else would flow. That morning, Murray made the call. Over Eccles's screaming objections, over protests from the entire engineering department, over dire warnings from Boeing's legal team about liability if the wings failed in combat, Murray ordered the new rivet pattern implemented across all production lines, effective February 25, 1942. He gave Frank Szymanski a $40 a week raise, a fortune at the time, and the brand new title of Production Methods Specialist. He gave Hendricks a promotion to senior supervisor. He told Douglas his job was safe. And he told Eccles that if he didn't like it, he could personally explain to General Hap Arnold why Boeing was still only building 14 bombers a month. The results were staggering. In March 1942, Boeing Seattle delivered 47 B-17s. In April, 91. By June, they hit 186 aircraft in a single month. But the real explosion came in July, when all 42 wing stations were fully converted to Frank's pattern and the workers had mastered the new, chaotic-looking sequence. July production, 284 B-17s. August, 319. September, 362 bombers rolled off the production line in a single month. That was more than the entire annual production of 1941. The impact on the air war over Europe was immediate and devastating for the Luftwaffe. In October 1942, the 8th Air Force flew its first mission with over 100 bombers, hitting industrial targets in Lille, France. The Luftwaffe had been built to fight defensive battles against small raids of 20 or 30 bombers. They could swarm those small formations, pick off stragglers, and make every mission costly enough to be unsustainable for the Allies. But 100 bombers? The defensive fire from that many B-17s, each bristling with 50 caliber machine guns, created overlapping fields of fire that made fighter attacks suicidal. German pilots called it the Verteidigungswand, the wall of lead. They'd lose 3 of their best fighters just to shoot down one bomber, and the Americans just kept coming day after day. By January 1943, the 8th Air Force was flying missions with 300 bombers. By summer, 500. Each one of those aircraft represented 2 hours of riveting time instead of 20. Each one carried 4,000 pounds of bombs deeper into Germany than Hitler ever thought possible. The legendary Schweinfurt-Regensburg missions in August 1943, the daring raids that crippled German ball bearing production and brought the Nazi war machine to a grinding halt, required 376 B-17s. Without Frank's pattern, Boeing wouldn't have built that many bombers in total by August 1943. The entire strategic bombing campaign, the single greatest effort that drew German fighters away from the Eastern Front and forced the Luftwaffe into an unsustainable war of attrition, depended entirely on Boeing's ability to flood the sky with flying fortresses. And it wasn't just Boeing Seattle. By April 1943, the Boeing plant in Wichita, the Douglas plant in Long Beach, and the Lockheed Vega plant had all adopted variants of Frank's revolutionary pattern. Combined production across all facilities hit 512 heavy bombers in a single month. The Germans were producing 1,000 fighters a month to counter them, but it didn't matter. You can't win an air war when the enemy builds bombers faster than you can possibly shoot them down. Frank Szymanski never became famous. He received a War Production Board commendation in July 1943, a simple certificate signed by someone he'd never met. It hung in his daughter's bedroom until she moved out in 1959. Boeing gave him that raise and the fancy title, but after the war ended, the Production Methods Specialist positions were quietly eliminated in the 1946 workforce reduction. Frank went back to Detroit, worked at a Ford plant for 23 years, and died in 1971, likely without ever knowing that his simple, scribbled rivet pattern had fundamentally changed how aircraft were manufactured forever. Because it did change everything, not immediately and not obviously, but the principle Frank stumbled upon became doctrine. In 1947, when Boeing began designing the B-47 Stratojet, their first swept-wing jet bomber, the engineers didn't just start with theoretical rivet patterns. They started by consulting with assembly line workers about access points and workflow. The B-47's wing used a pattern that looked chaotic on paper, but could be riveted by 6 workers simultaneously in just 3 hours. Nobody called it the Szymanski method. Nobody even knew there was a Szymanski. They just knew that matching rivet patterns to the reality of assembly, instead of to pure structural theory, produced better aircraft faster. Douglas aircraft applied the same principle to the DC-8 in the late 1950s. Lockheed used it for the legendary C-130 Hercules. When Boeing designed the 707, their first revolutionary commercial jetliner, the engineering team included assembly line supervisors in the initial design reviews. It was a revolutionary concept. Ask the people who will actually build the thing whether the design is, buildable. The 707's fuselage panels used what Boeing internally called cluster riveting, which was Frank's pattern with a fancy corporate name attached. It cut the 707's fuselage assembly time by 60% compared to the Stratocruiser it replaced. Frank's real legacy showed up in modern aerospace manufacturing philosophy. There is a core principle called Design for Manufacturability, or DFM, that every single aerospace engineer learns in school now. It states that a design's elegance is measured not just by its performance, but by how efficiently it can be built. And the textbook example, taught at MIT and Caltech and every aerospace engineering program in the world, is the B-17 wing riveting crisis. They teach how a theoretically optimal pattern proved inferior to a practically optimal pattern. They teach how reducing assembly time actually improved quality instead of degrading it. Most students never learn about Frank. They learn about Boeing's innovative production methodology development program, as if it was a committee decision born in a boardroom. Modern aircraft like the Boeing 787 take this concept even further. The 787's composite fuselage sections are joined with computer-designed fastener patterns that look completely random to the human eye, but are perfectly optimized for robotic installation. Each pattern is generated by complex algorithms that consider structural loads, assembly access, thermal expansion, and 20 other variables simultaneously. Frank did the exact same thing in 1942 with a pencil and the back of a time card. He just didn't have the math to prove why it worked. He had something better. He had pattern recognition, developed from watching thousands of rivets get installed and noticing with agonizing clarity what slowed everyone down. And that's the uncomfortable, beautiful truth this story reveals. Frank wasn't smarter than Boeing's brilliant engineers. He wasn't better educated. He didn't understand von Karman's complex stress equations or load path analysis. What he had was a different kind of knowledge. He knew how tired you get crouching in the same position for 40 minutes. He knew how pneumatic hoses tangle when workers have to cross paths. He knew that theoretical perfection, executed poorly, produces far worse results than theoretical imperfection executed flawlessly. Boeing's engineers knew how to calculate stress. Frank Szymanski knew how to actually build things. Both types of knowledge were essential to winning the war, but only one type was valued. The aerospace industry eventually figured this out, but it took decades. Modern aircraft development now uses integrated product teams, where machinists and assemblers work alongside engineers from day one of the design process. When Airbus designed the A380, the largest passenger aircraft ever built, assembly line workers literally had veto power over design decisions that would make manufacturing difficult or impossible. That is Frank's real legacy, not the specific rivet pattern, which is now obsolete in an era of automated fastening systems. His legacy is the idea, the simple, powerful, and often forgotten idea, that the person doing the work might just understand the work better than the person who designed it. It was revolutionary in 1942. It should be common sense now. Except we keep forgetting it and having to relearn it over and over again. Every great innovation cycle produces its own Frank Szymanski, someone on the ground, in the trenches, who sees the obvious solution that the experts are too educated, too experienced, too brilliant to notice. The smart organizations listen. The rest keep riveting their wings in 20 hours and wondering why they're losing.